Good evening everyone, I'm Mr. Ish. You are joining me for this derivative of ellipse curve video. Thank you for joining me. I hope everyone's having a nice day. If you look at an ellipse which is directed horizontally about the origin, you know this x square over a square plus y square over b square represents the equation of that form of an ellipse. A standard equation ellipse which is horizontally directed, and your ellipse would look something like that. You'd have a vertex here at minus a comma 0 and a comma 0. You'd have a minor axis endpoint here at 0 comma b and your 0 comma minus b. That would be your minor axis, and this right here would be a major axis. But if you're looking at that specific curve, you could be able to do a derivative determination at every point on that ellipse curve, or maybe not. We have to find out where you cannot do a good derivative determination. If you are to do derivative determination, you'll have to do some sort of differentiation of this. You might as well convert this into a better form. You don't have to, but you could. You could do a good common denominator, and you can do x squared b squared plus y squared a squared is equal to a squared b squared. I've done the common denominator and I cross multiplied with 1, and there it is. And now if you want, you can do implicit differentiation of this, and you would get here b squared x. The derivative of this would be b squared would be like a coefficient of x squared. You'd push it out and you'd have a 2x b squared or 2b squared x. Here you generate a 2a squared y by dy dx. I'm just doing implicit differentiation over here because I want to get both the x and the y values involved. The derivative of a constant here is a 0. You're going to solve here for dy dx, and you're going to push everything on the other side. You'll get minus 2b squared x divided by 2a squared y. The 2's will cancel out. You'll have minus b squared x divided by a squared y. This right here would represent a good derivative factor, or your implicitly derived derivative factor, into which now you can put the values of x and y. You have good values of x and y. In each of these instances, the coordinate pairs, you know what the x and the y values are. You can just take this right here, value 0 comma b. At 0 comma b, you could very well visualize a horizontal tangent line, and you know the slope of that would be 0, but you could very well plug this right in here. Here's your x value, here's your y value, and see what happens. You'll have a minus b squared times your x value, which is a 0, divided by a squared, and then your y value here is b. You'll have a 0 divided by a squared b, which is a 0. So here, the tangent line right over here would be horizontally inclined, and you know, well, we should not even use the word inclined because inclined represents some sort of a slope, but a horizontally placed line has a derivative of 0. So we know that right there looks good. How about right over here at this point right here, this vertex, minus a comma 0? Well, we have a minus a comma 0. We can again plug it right in here. Here's your x value, here's your y value. You can do minus b squared times minus a divided by a squared times y value here, which is 0. Here you end up getting a b squared over 0, which is undefined because you end up getting a vertical tangent line. You can visualize here again, our tangent line over here would be vertical. You would have a horizontal tangent line right over here, and you'd end up having a vertical tangent line here. So at the vertices of the ellipse, you will have a non-differentiability occurring over there. That is, you cannot differentiate the vertex of either vertex of this ellipse here, but you can certainly do a good derivative determination here at the minor end points, right, at the minor axis endpoints, and then of course you should be able to do a good derivative determination at any other point on the curve, anywhere in between. For demonstration purposes, if you very well blow up the ellipse, and you don't have to be so specific over here, and we're looking here at the ellipse looks like that, at any point from right over here, you can say here from minus a going up to 0, at any point from minus a up to 0, you'll have all of these tangent lines, which will always be in some degree positive tangent lines. Then when you're going from 0 up to a, right here, here's my a comma 0, and you're going from 0 up to a, you would have tangent lines which are declined downwards having a negative slope. The only reason why I'm not including 0 here, nor am I including the a values, which is why I have the circular parentheses in both cases, because we know here at the tip, here at the top and the bottom, and here at the extreme ends, we've already shown you the slope over here is always equal to 0, slope here is equal to 0, the slope here at the ends are undefined, and you know that to be the case. I've shown it to you. Then you're looking here again from minus a comma 0, but looking down over here, you're going to end up seeing negative tangent lines, having negative slopes over here. Then of course here from 0 going up to A, not including either of those values, you're going to have positively inclined tangent lines in all instances. So you see how there's this bit of a reverse effect which comes into play. From minus A to 0, you have both positive and negative tangent lines occur based on which side of the curve you're looking at, and then from 0 to A, you have both negative and positive tangent lines again occur based on what side of the curve you are on. So the derivative of ellipse curve can very well be represented here by this specific form over here. If hypothetically you did not go to this denominator determination and then you go that route and you just did implicit differentiation of this specific curve, let me show you. In this instance, when you're just doing the implicit differentiation of just this entire equation, x squared over a squared plus y squared over b squared is equal to 1, right? You're doing all of that in terms of its derivative. You can look at 1 over a squared then d over dx, x squared, plus 1 over b squared then d over dy, y squared dy over dx, and the derivative of 1 is a 0. You can look at it this way. You'll have 2x over a squared. Here you'll have a 2y over b squared dy over dx is equal to 0, and then you can solve this out and see what happens. You'll have a 2y over b squared dy over dx is equal to minus 2x over a squared. You would have to take this part right here on the other side and it would have to divide. Dy over dx is equal to minus 2x over a squared divided by 2y over b squared. And then do this fraction algebra, you'll flip the denominator and you'd get minus 2x over a squared times b squared over 2y. And you can simplify all of that and look what you get. You get a minus xb squared over a squared y. And that's exactly what you're seeing right over here, except here I wrote the b squared first and the x, it doesn't matter. The instances here are both the same. The instantaneous rate of change, the derivative or the implicitly derived derivative factor are the same in both cases. You don't have to go through this longer or perhaps a more difficult route. Just do the direct implicit differentiation of this equation that you see. Anyhow, the purpose of this video here is to show you the derivative of the ellipse curve. The ellipse curve has a derivative at all points except for 2, and those 2 points are right here at the extreme ends, right at the vertices, and that right there is for the vertices of a horizontally oriented ellipse. You can determine here that for a vertically oriented ellipse, which would have the equation as this, x squared over b squared plus y squared over a squared. In this instance, the vertices are here at the very top. You'll have a positive a over here and you'll have a minus a over here. The vertex here is at the top and the bottom, and the minor axis endpoints, or your minor axis, has a horizontal orientation here, minus b comma 0 and a b comma 0. Now in this instance, the non-differentiable areas are 2, just like here they're 2, but here it's not at the vertices. Here it will be at the minor axis endpoints, and here the vertices are very well differentiable, except they'll be horizontal tangent lines. So you see there's a flip here. With regards to the horizontally oriented ellipse and the vertically oriented ellipse, you have 2 areas which are not differentiable. For this, they happen to be at the vertices. For here, they happen to be at the minor axis endpoints. And you can see from there and extrapolate from there and make your own conclusions. Thank you for watching. Stay tuned. Have a nice day.